In the last class, we were discussing about the time response analysis of the first order system, and ultimately what we have observed that, say, this is your time, this is your amplitude, and we get the output characteristic curve is like this. Say this is your input, this is your 1.0, that is your input signal, and output curve was like this. That means steady state error was 0. So steady state error was 0 for the step signal. First order system, when applied a step signal at the input side of it, you get the step response. So this is the output signal. Now see how I have drawn the curve. This curve is drawn based on the formula 1 minus e to the power t by t. This is your CT. See, what is this t? This is t is known as time constant, right? So what is the function of this time constant? This time constant plays very important role. Like, say this curve may not be like this. This curve can be like this also. Steady state error is 0. That means this output curve will exactly same as the input curve after certain time, right? And this curve may be like also. So what is the difference we get from here? We get steady state error is 0 here. Say this is time t1, this is for blue color, this is time t2, and this is for green color, this is time t3. And in all three cases, you see this output is exactly following the input, and after certain time t1, t2 and t3, you will get the exactly same input or the desired value. That means steady state error in both the three cases are same. So what is the difference? You see this part, e to the power minus t by t. So if the value of t is high, what happens? See, the nature of the curve is like this. In this case, this is the nature of the curve, right? And this may be the nature of the curve, this may be the nature of the curve, and depending upon the nature of the curve, e to the power minus, this is e to the power minus t by t, this is also e to the power minus t by t, this is also e to the power minus t by t curve. So once the value of t is much more, that means the value of t, which is known as the time constant is higher, that means it requires the curve to be like defined, and for defined values of t you get the defined values of time e to the power minus t by t. So in all the three cases you have to subtract this curve from the value of 1, right? So what you get, if the value of the curve is like this, so definitely 1 minus this curve will be right this. So surprise, once the curve is like this, e to the power minus t by t, so in that case curve will be like this, and once the curve is like e to the power minus t by t, so this will be like this. So this is the actually fundamental concept of time constant. So if you vary the time constant, basically the system response is either stiffer or sluggish in nature. So sluggish in nature means it will take much time to reach the desired value, and if the response is faster, that means the curve of the output curve is looking like this. That means on a faster time, that is smaller time of t1 or t, you get the desired output. So this is the variation of the time constant, and depending upon the time constant you will get the different types of output signals. That means how it reaches the desired value, that is how fast actually the output curve tracking the input. That is the actually physical significance of this time constant. Now I'm going to discuss in detail about the response of a standard second order system, right? We are going to discuss about the response of a standard second order system. So distance of the standard second order system means you have to find out the CS again. CS. So you have to find out the CS, and RS is here also step signal, because we have already written there response of a standard second order system, and in all cases we will apply the step signal, and RS is taken as step. So RS that means is 1 by S, that means Laplace transform of RT equal to 1. So if you get the Laplace transform of it, you get the RS, that is 1 by S. This is the step signal. Now how the standard second order system is looking like? So for that I am writing here one basic block diagram. This is plus minus, and this is your omega n square by S into S plus 2 xi omega n. I will discuss in detail about the parameter I have written here, like omega n xi. So this is your CS, output signal, and unity feedback control system. This is unity feedback. So HS is equal to 1, and once HS is 1, and this is your GS, so you get the closed loop transfer function of the system CS by RS equal to GS by 1 plus GS into HS. You know this. So based upon this, if you put this value HS is equal to 1 and GS is equal to this, what you get omega n square by S square plus 2 xi omega n s plus omega n square. So this is your CS by RS, right? So this is the closed loop transfer function of a second order system, and this system is to be analyzed by some mathematical formulations. We write CS by RS equal to omega n square by S square plus 2 xi omega n s plus omega n square. So what is this omega n? And this omega n is known as natural frequency of oscillation, right? And this xi is known as damping factor. And why this damping factor is so important? Because you see, this is a second order system, no doubt, because the power of S in the denominator is 2. So this is a second order system, and second order system means there will be two poles, right? If you solve this, you will get the two poles. Now the locations of the two poles in the S plane plays very important role. Now what is this damping factor? Damping factor means say there are three kinds of damping normally applied to any system. For example, I write like this. Say this is t is equal to 0, this is time, this is amplitude. Now this is your say 1.0, this is your step signal. Now if there is no damping, so what could be happening? That means the system response is like this. How the system response is like this for a second order system, that mathematical formation I will show you. Now this is your when the curve when that is natural oscillation. When there is natural oscillation, you see from this mathematical formulation what happens. Just note down denominator part, characteristic equation. We say is characteristic equation, that is S square plus 2 xi omega ns plus omega n square, and we have already just nominated or terminology is such that the natural frequency of oscillation is omega n. Now when this damping ratio or damping factor is what? That means when you are applying certain kind of damping, you can read it in some measurement chapter that damping is essentially to reduce the oscillations. You see the oscillations means this magnitude of the oscillation, that means lower part and upper part, that is fixed type of amplitude. This is oscillating in natural oscillation. Now when you apply certain kind of damping, say air damping, electromagnetic damping, water damping, whatever different kinds of damping is available, if you apply this, actually your aim is to reduce these oscillations, right? So initially, if there is no damping, ja is equal to 0, means no damping. So how the characteristic equation will be looking like? So this equation will take the shape s square plus omega n square, right? So you will get only the parameter omega n, there is no damping part. So this will be like this. And how this will be like this, that I can show you the in respect to the locations of the poles later on. And next, what happens if you apply certain kind of damping? Say damping means greater than 0. So what happens, these oscillations may not be like this. So these oscillations may be like this. So this is trying to reduce, right? This value xi greater than 0. Now depending upon the damping, whenever you are applying damping, there are also different types of damping. So different types of damping are like this. You see xi greater than 1, number 2 xi equal to 1, and number 3 xi less than 1 but greater than 0. So xi less than 1, and this with respect to 1, these three types of damping are normally denoted. If the value of xi is greater than 1, that means it is assumed that the damping is very much higher. And once you have applied certain type of damping which is very much higher, so what happens, suddenly these oscillations is reduced, and you get this actually response curve is like this. So actually what happens, suddenly your oscillation, that means your transient part, this is known as the transient part, already we have discussed. Transient section means what? Means there is certain oscillations, and transient part is dies out suddenly if the value of xi is greater than 1. So that is known as over damping. Next, xi is equal to 1. So xi is equal to 1 means then also you just get this curve is like this. So this is known as critical damping. This is known as critical damping. There also you will get almost transient is 0. So transient analysis cannot be done for the system which is having the over damping behavior and critical damping behavior. So for the system which is having over damping and critical damping behavior, you cannot be able to obtain the transient parameters. And what are the transient parameters? You see TR rise time, already we have discussed, TP peak time, TS settling time, and percentage peak overshoot. These are the transient parameters, and these parameters are very much essential for designing of any control system. So we need to have this transient. So in order to have the transient, the damping is so provided such that damping can be minimized, but there is certain types of oscillations, not exactly zero oscillations. So you can see it, or I can give you this curve is like this. So this is xi less than 1, and this kind of damping is known as under damping. So these are all about the damping behavior of any system. That means you can have over damping situation, you can have critical damping situation, you can have under damping situation. But for the analysis of control system, what we need to have a system which is actually possessing the under-damping behavior, and once the under-damping behavior is there, you get the steady state section as well as the transient section. And transient section, if you get, you can measure these control system parameters like TR, TP, TS and percentage MP. So that is why this type of damping is considered for the analysis of second order system when subjected to step signal. Now let me explain what are the defined actually mathematical formulations which is related with this type of dampings, right? So we get the characteristic equation of second order system. You see this is 1 plus GSHS equal to 0, that could be obtained from the denominator. That means SS square plus 2 xi omega ns plus omega n square is equal to 0, right? So if you solve this, you get S equal to minus B 2 xi omega n plus minus B square 4 xi square omega n square minus 4ac omega n square into 1 by 2a. That means minus 2 xi omega n plus minus 4. So you get 2 out of here. That is your omega n square and xi square minus 1 by 2. So you get 2 common out of here. So minus xi omega n plus minus omega n root over xi square minus 1 by 2, right? See the two pole locations, as this is a second order system, so definitely we will be having two poles. So what are the two poles? Say S1 is equal to, sorry, this will be 1 minus xi omega n plus omega n root over xi square minus 1, and S2 equal to minus xi omega n minus omega n root over xi square minus 1. These are the two pole locations, right? Now what happens? The defined conditions we will have to take, right? See, first case we will consider the value of xi is equal to 0. Sorry, yes, the value of xi is equal to 0. That means undamped. Undamped means natural frequency of oscillation. That means this is oscillatory in nature, purely oscillatory, no damping is applied. So if you put this value xi is equal to 0, what happens? The locations of the pole, you see, S1 is equal to, this part is 0, this part is 0, so this is omega n, and this is also 0, and this is also 0. So what is happening? This is root over, that means omega n root over minus 1, and S2 is equal to omega n root over minus 1. So that means minus j omega n plus, sorry, minus j omega n. What you will see? This is the two pole locations. One is only imaginary value, other is only imaginary value, but the defined sign. So if you want to get these locations in the S plane, just write the S plane. What happens? This is your S plane. So put this value there. This is plus of j omega n. Omega n is the natural frequency of oscillation. That means when there is no damping, what is happening? The poles are located here, that is plus j omega n, that is minus j omega n. That means the poles are locating on the imaginary axis. Now already we have discussed. So if the poles are located on the imaginary axis, the system is oscillatory in nature. Oscillatory in nature. That is the condition for the oscillations. That means the poles are located on the imaginary axis. Now at omega xi is equal to 0. Now next part, see, if the value of xi is equal to 1, that is the critical damping situations. If the critical damping situation occurs, xi is equal to 1, that means this put the value of xi is equal to 1 here at S1 and S2 location. You see, this becomes 0, this becomes 0. So S1 and S2, S1 is equal to minus xi omega n and S2 is equal to minus xi omega n. So what you will get, the two poles S1 and S2 are in the same positions and they are only the real values, they are on the same positions. And if you place this in the S plane, so this is your S plane, what will happen, these two poles are located on the minus of real axis, so whatever be, this is double pole minus xi omega n, right? This is for the critical damping situations. Now coming to the third position, if the value of xi is greater than 1, that means over damping situations. If the over damping situation occurs, you see this xi square minus 1 is positive, this is xi square minus 1 is positive. So the S1 is having minus xi omega n plus omega n root over xi square minus 1, and S2 is equal to minus xi omega n minus omega n root over xi square minus 1, right? Xi square minus 1. That means these are the two different values of the poles, and these poles are real in nature. These poles are real in nature. Now the third case is that, fourth case, the value of xi is less than 1. This is very important, and this part is related to our analysis. So this is known as the under damping situations. When the xi is less than 1, what happens? You see the pole locations, right? Pole locations are right. And now the conditions we are discussing, xi is less than 1, that means under damping situation. And in this condition, if you put the value of xi is less than 1, what you will get? This S1 is equal to, say, minus omega n plus root over xi square minus 1, that is negative value. So we get minus of 1 minus xi square. Similarly, S2 will be equal to minus xi omega n minus omega n root over minus of 1 minus xi square. As the xi is less than 1, we can convert it like this. So what we get, this is nothing but, so S1 is equal to your minus xi omega n plus j omega n root over 1 minus xi square, and S2 is equal to minus xi omega n minus j omega n root over 1 minus xi square. So what you see, these are the roots having the complex roots. These are the complex value, and the roots are complemented to each other. That means the complex conjugate to each other. If you put these values in the S plane, see what happens. This is plus j of this, this is minus j of this. That means one pole may be located here, so simultaneously the second pole must be located here. So these are the locations of the poles, and you see in the normal system to be stable, the poles which are located on the left hand side of the S plane are stable. And you see, when the value of xi is equal to 0, the poles were located in these positions, and when the xi is less than 1, the poles are located here, and the value xi was 1, what happened? The poles are located on the minus xi omega n. That means the real part of this part. See, real part of these two poles are same, and that is again equal to the real pole locations when the value of xi was 0. This is your minus xi omega n, right? Actually this is the way how the roots are moving when the value of xi, that is damping, is changing. That is the criteria actually you have to know. And you see, if this is your minus xi omega n plus j omega n root over 1 minus xi square, so this is your minus xi omega n minus j omega n 1 minus xi square. So actually if you just get the real part of it, what is the real part of it? This real part of it, that means this part is minus xi of omega n, and imaginary part of it is equal to omega n root over 1 minus xi square, right? And if you just join this line from origin to these positions of the pole, what will you get? This is your angle theta, say for example. So if this is your theta, so you get tan of theta. What is the tan of theta? Tan of theta is equal to omega n root over tan theta is the angle you see here, and this is your magnitude xi into omega n. So tan theta will be equal to omega n. You see this is your omega n root over 1 minus xi square by xi into omega n. So you get tan theta root over 1 minus xi square by xi. This is your tan theta. So theta is equal to tan inverse of this root over 1 minus xi square by xi, and from this you get the value of cos theta. Cos of angle of this equal to xi. So cos theta is equal to xi, or in other words you can say theta is equal to cos inverse of xi, and this angle is known as damping angle, and this damping angle plays very important role when we will discuss in future the Rule-Lucas plot. So damping angle will play very important role, and see this damping angle is directly related with the damping ratio xi by the formula theta is equal to cos inverse xi. So this is how the damping the different damping phenomena, like starting from the oscillatory behavior with the no damping was there, from the critical damping, the under damping and over damping situations, you get the defined pole locations, and from the defined pole locations you see when these poles are on this imaginary axis, that means the oscillatory nature that actually happening here. When there is no damping, xi is equal to 0. When you are changing the damping from minus less than 1 to greater than 1, you see the locations of the poles is like this, and corresponding to the damping angle you get. Now I am going to discuss about the step response analysis of a standard second order system.